Alrighty, welcome back. So this is lab 3 for physics 2211, and this is about oscillations. So just an introduction here. So the purpose of the lab is basically to track and analyze a video of a object oscillating in two dimensions, so both the x and y dimension. And then we're going to compare this to a program simulation that we write and basically make to model the same thing, but just without the error of it being a human lab. And so we're going to plot and analyze the differences in the energy changes and the motion itself, and then compare those. And so what we end up finding, just as a little sneak peek, is the two models follow very similar paths, but the computational one is just a little bit more accurate with higher peaks and more consistent motion. So here's some key concepts. So we just have Newton's second law, which is F equals ma, or in this case, momentum principle, which is delta P over delta T is the force, and velocity update position formula, or velocity update formula, and the position update formula, which we've been over multiple times. And then so we're comparing the spring when it's at the top here to the spring when it's at the bottom. That motion is what's going to change the amount of energy in the system, and that we're going to find with a bunch of these equations. So the kinetic energy equation, 1/2 mv squared, gravitational potential, which is mgh, and then lasting potential, which is 1/2 k L minus L naught squared. So all those energies add up to the energy of the system, and then the change in energy of the system from initial to final is the work. So the experiment itself, I tracked this video right here. You can see the tracker software right here. And here's the initial conditions right here. So all this is given to us already. So the length of the spring is 0.7 at static equilibrium. The mass and the K is given. And then the initial position is what I found to be somewhere up in this position, which is I found to be these coordinates right here. And then no outside work is done on the system, which means all of the changes in energies added up is always zero the whole time. So we're going to get into that more a little bit later. So I tracked this frame by frame, the position of the object, and then I converted it to a CSV file or comma separated value file below, which this is a little excerpt of it right here. This is the first value. So the simulation itself, this is all the code that I changed. So basically, the mass, position, gravity, all this stuff is basically givens. Like I was saying earlier, like back in this slide, all these equations is what we use to get right here. So you can see here's the energy ones, and here's the spring, and here's gravitational constant, stuff like that. And then over here is where it actually tracks it. So we have basically define all the initial energies, and then the gravitational force, the spring force, and the net force, which is, of course, net force is spring plus gravitational, and those two are going to be, this is basically in the y direction going downwards, m times g, and then the spring force, which is, like I said earlier, k times s times L hat. And then this is basically adding up all the energy changes, and that's what's going to plot onto our energy graph. So this is what it results in. So the model is the blue one, and then the experiment is the red one. And so you can see they follow very similar paths on the X. This is the X side, and this is the Y side. So the X path is very, very similar. The only difference being the peaks on the experiment are a little bit lower, and they start falling a little bit behind at the end. And that could be because of a little bit of friction or air resistance that the model doesn't count for, but the experiment does. And then same thing with the Y. It's a little bit less pronounced, but you can see it does start to fall behind here at the end, and it's a little bit lower, just slightly. Same thing there. It's more about probably some friction or a little bit of human error. Then here's the energy comparison. So you can see over time. So when one of them is at its peak, the other one's at its minimum, and same thing, vice versa. So the green line is the spring potential energy, and the red is the gravitational. So like I said, they inverse each other, and then the delta E stays constant the whole time at zero. Like I was saying, there's no work done on the system, which means the change in energy is going to stay at zero throughout. So to answer the question, what does this mean? Is the energy principle satisfied? Yes, as the delta E line, which is this red or orange one, stays at zero the entire time. And then another thing, what does it mean? The observed period in the X and Y direction. So I found both of those to be 1.14, 1.614 and 1.519, which they're a little bit different, which you wouldn't necessarily expect it to be, but they are. And this is because, like I said, possible source of error over here, human error in tracking the object, friction, or air resistance, among other things. And that could possibly lead to this difference right here. But the main thing is we use 1K value for both directions, the X and the Y. when in actuality they would probably have different K values, and that's why the periods were found to be different overall. And that is pretty much it. Thank you for watching.